Welcome! If you're an engineer working on IoT devices, you're in the right place. We're about to dive into a really powerful combination for high-performance designs, the reconfigurable loop antenna and the MIPI RFFE control interface. Okay, just look at this. The big question for any IoT engineer today is how do you get true global connectivity into a device that's getting smaller and smaller? The answer, as you might guess, lies in a much smarter antenna. And that brings us right to our first section. So let's start by framing the problem, what we're calling the IoT antenna dilemma. Look, the market demands everything, right? Global coverage, which means supporting a ton of bands like NB-IoT and LTE. But at the same time, product designs are constantly shrinking. You've got this fundamental conflict. You need more antenna performance, but you have way less space to work with. Your traditional antennas, they just can't keep up. So how do we get out of this jam? Well, let's take a look at the hardware that makes it all possible. And here it is. This is the Abracon niche antenna. Yeah, it's compact and super efficient, but its real power, its secret sauce, is that it's reconfigurable. Its unique shape also gives it these great magnetic radiation properties, which means it's incredibly stable even when it's crammed right up against plastics and other components inside a tiny device. So, how does it pull this off? Well, instead of being just a static piece of metal tuned to one frequency, this design can actively change its electrical properties on the fly. It's not one antenna, it's basically multiple antennas packed into one, all thanks to some really clever electrical reconfiguration. And this diagram just illustrates the mechanism so brilliantly. The antenna's operating frequency is all determined by the capacitance on its top load. So you just use a simple RF switch, in this case, a single pole, 4-throw, to connect different capacitors to it. And just like that, you're retuning the antenna on the fly for whatever LTE or NB-IoT band you need. It's that elegant. Okay, so we have this fantastic, tunable piece of hardware. The obvious next question is, how do you control it? That brings us right to the control interface.
You've really got two main options here. The old school way is GPIO. Think of it like a bank of simple light switches, just on or off. It works, sure, but it's pretty basic. On the other hand, you have MIPI's RFFE. This isn't a light switch. It's a modern, digital control bus that was standardized specifically for RF front-ends. It gives you sophisticated, two-way communication, letting you send complex commands and even get diagnostic data back.
And that really is the key takeaway. As EE Times points out, the RFFE bus was literally built for the complexity of modern RF systems. With all the real-time tuning and multiple signal chains we have now, it's become the clear industry choice. It is purpose-built for this job. You know, the performance of this entire amazing system, it really hinges on one tiny component, the RF switch. So let's take a closer look at what makes a good one. Okay, first up, RON, or on resistance. The crucial point here is you want this number to be as close to zero as humanly possible. Any resistance, even a little bit, acts like a tiny resistor in your signal path. It wastes your precious signal strength as heat, and, you guessed it, it drains your battery faster. For low-power IoT, minimizing that loss is absolutely everything. And on the flip side, you've got COFF, or off capacitance. This is all about isolation. When a switch path is off, you want it to be truly off, not leaking signal over to other parts of your circuit. Better isolation means a cleaner signal and ultimately way more reliable performance. Now, this is where it gets really interesting. Check out these numbers for RF MEMS switches. An on resistance of just 0.8 ohms? That's incredibly low. They run at around 3 volts, which is perfect for standard IoT batteries, and the power consumption is tiny, around half a milliwatt. For any battery-powered IoT device where every single joule of energy counts, this is a perfect fit. All right, we have the antenna, we have the switch, we have the control bus. Now let's put it all together. And this final section is a really practical guide to help you avoid a super common pitfall during integration. So you've designed everything in, you power up the board, and nothing. The MIPI RFE bus won't talk. It is an incredibly frustrating moment that a lot of engineers run into. So let's look at exactly why that happens. The problem almost always comes down to this: floating impedances. The MIPI spec is very clear that the bus master, your transceiver, is supposed to have an internal pull-down resistor to keep the bus in a stable, low state when it's idle. But the reality is, not all transceivers actually do this correctly, and that leaves your data and clock lines in this undefined, floating state.
And this floating state is a huge problem. An unexpected noise spike on the clock line can easily be misinterpreted by the slave device. And for modern switches that use these lines for advanced functions, like swapping their unique slave ID, this can cause the device to literally change its own address. Once that happens, it's impossible to talk to it. It's game over.
Thankfully, the fix is both simple and totally robust. You just add your own external pull-down resistors, usually something around 100 kiloohms. This guarantees that the bus lines are held low when they're idle, giving you a stable electrical state and securing reliable communication, even if your master device is missing those internal pull-downs. So to wrap this all up into 4 key steps, here's your path to success. 1. Start with a reconfigurable niche antenna for that compact multiband magic. 2. Pair it with a high-performance, low-RON, low-cough RF switch. 3. Use the industry-standard MIPI RFFE bus for control. And 4, the crucial one. Make sure that bus is electrically stable by adding pull-down resistors if you need them.
You know, this combination of antenna, switch, and control protocol isn't just an upgrade, it's an enabler. What you should really take away from this is a clear blueprint for building smaller, smarter, and more capable connected devices. The real question is, now that you have the tools, what are you going to build?